So in the first section of chapter 3 on node voltage analysis, we demonstrated a technique for finding the voltages and currents for resistances when their arrangement is not in series or parallel. And we did that in ways by defining nodes, areas of the network for which we can use the representation of currents, remember, and using KCL to be able to produce equations that involve those nodal voltages and be able to produce a linear system that will, hopefully unique system with independent equations to produce those node voltages. We're going to do the same thing with a technique called supernodes, where we're simply looking at those currents again, but this time not the current of any individual node, but in terms of a whole block of nodes, or in this case, of a closed surface, because you can because KCL will apply for a grouping or a blocking of the components as well, all right? And so below, you're going to see representations of this, where we have a little bit more complicated situation because we have these two voltage sources now sandwiched in between our various nodes. You have node 1, node 2, node 3. But I want to point something out when you have the circumstances of the interpretation now of what's the relationship between these voltage sources and these nodal voltages. Well, if you think again of voltage, occurring across a resistance, well, you can also think of it in terms of how the voltage changes from one part of the circuit to another. And for example, if we were doing a current flow and coming into the negative pole of this voltage source, we know the voltage source is going to generate or supply voltage energy, to the rest of the circuit. So whatever the voltage is here, okay, we're going to, add 10 volts to it to get to node 2, all right? Or another way of saying that, interesting enough, is the differential between those two node voltages. In other words, that V2 minus V1 has to be 10 volts, okay? Or another way I just said that was that whatever the voltage is at V1, you're going to add 10 volts to it, right? And then that's going to give you the voltage at V2, right? And so if you just subtract V1 from both sides, you get both equations, okay? This is 10 volts, right? So you could look at it the way we did for representing the currents before. In other words, you from V1, you could look at it this way: of V2 minus V1 has to be 10 volts, right? But the idea is that this is going to, assuming from left to right, as you go from V1 to V2, you're going to be adding 10 volts, okay, to whatever the voltage was at that part of the circuit, okay? Hopefully that makes sense because it's distributing energy, all right? So that's a relationship. Now you could also have gotten that from KVL as well. So, so that's another way of looking at it. If we were to represent a KVL loop here, okay, going clockwise, same thing would happen, because remember, if we represented the polarities for these nodal voltages using our arrows away from, negative here at the reference node, but positive at the node, and then same thing for V2. There's another reference arrow, plus, minus. And then as we're traveling, say in a KVL sense, if we hit the head of that arrow, we get a positive voltage. If we're coming up through the tail of it, then we're negative. So if we were going clockwise here, for example, we would hit, I'm just sort of illustrating that we'll get this equation either way. So if we were doing KVL in this loop here, we're going to get negative V1, okay, coming into the negative pole, minus 10 volts of the voltage source, and then plus V2 at the top there, plus V2 equals 0, okay? And so if you look at that very carefully, that also says that V2 minus V1 equals 10, which is the same thing we had there, okay? So either way, you can look at it either from a KVL standpoint using the reference node, or just this idea that you're incrementing or decrementing the voltage as you move through the network from one node voltage to another. What about over here? This is interesting because this actually could be more useful. Anytime you see a situation where you've got this node here, nodal voltage here, and then you've got it directly connected to a voltage source going to ground. So we know something here. We don't necessarily know what V1 and V2 are, but we know the difference between them is those 10 volts. Here we know the voltage is 0. So what's happening in this case is that we're getting V3, all right? Now notice the difference here, okay? You're getting V3, and this is going to deliver energy, so we're going to come into the negative polarity there, right? So we're going to add in 15 volts and then go to 0, all right? Because there's 0 voltage here, all right? So in this case, what this means is that the voltage at that node has to be negative 15 volts, okay? Because if we're in a clockwise delivery here, then this is going to deliver 15 volts. The only way you can get to 0, if this is going to add 15 volts to the circuit, is that must have been minus 15 volts, okay? So hopefully that makes a little sense there. Again, that's KVL as well. But again, you're going from a nodal voltage to 0, all right? And if you're going to add 15 volts, now you may say, no, wait a second, should I be subtracting 50 volts and this is positive 15 volts? Again, we're looking at it from the perspective that you're adding voltage to the circuit in this direction, okay, right? Okay, another way of looking at it, you could say, well, this is connected to the negative polarity of it, but I don't like that. I think the idea of going like we did here, think of the destination, subtract the where you started, and that must be equal to 10 volts, okay? Starting at this direction, this node voltage, you go from V0 to 0, excuse me, V3 to 0, that must be equal to 15 volts, okay? Right. So, oh, actually, sorry, I said that backwards. We're going from 0 to V3. So if we're going 0 to V3, okay, right, that has to be equal to 15 volts. Okay. Same thing here, V2 to V1, right? And in that direction, you're hitting the positive polarity there, okay? And the same thing here, you're hitting the positive polarity there. So you're going from 0 to V3, and that must be 15 volts, okay? Actually, that makes a little bit better sense, doesn't it? In some sense, because you could think about just the way we did polarities before. If we're representing voltage, 10 volts has to be represented going from V2 to V1. You're going into the positive polarity there. If you're going to generate 15 volts here, you're going from 0 to V3, okay? That differential has to be 15 volts, okay? So the nice thing to know here is that that's useful. You don't really need to have that V3 there. We actually know what the voltage is at that point because of its relationship to the ground with that voltage source, okay? All right, so what we'll do now is the idea of a supernode to try to make things a little bit easier to try to encapsulate currents without looking at the complexity of that voltage source there. We just combine the voltage source with those two nodes, and that's called a supernode. Okay. The funny thing is, you can do the same thing over here. This could be another supernode. The idea is, again, collapsing two nodes with a voltage source into one node, and that could be, say, supernode number 2. And what we're going to do is we're going to write the KCL equations for the supernodes. Same idea before. What are the outgoing currents coming out of those supernodes, right? So let's do KCL supernode 1, okay? And then we'll do the same thing for supernode 2. So again, you just look at, from the supernode's perspective, you have one coming up here, one there, one to the right, one to the bottom, and another one to the bottom, okay? So let's start with the ones going to ground. So this current coming out through the R2, right, is going from nodal voltage at V1 to ground. So what we would have is V1 minus 0, or just V1 over R2, again, using our NVA approach that we did last time. Same thing will happen here. This part of the supernode, whatever that voltage is there, V2, will go to ground, and we'll go through R4, so we'll go V2 over R4. Then represent the current, let's say coming up from the top, it will go from V1 to V3 through R1. Okay. And then, of course, we have V2 going to V3 through R3. However, remember, we just discussed the fact that, well, if you're generating voltage and what's coming through, if you're going from 0 to the voltage there at V3, you must be going through 15 volts. In other words, going from 0 to this V3, right, must be 15 volts. That's exactly what that equation says, okay? All right, so we can then substitute this into the equation and get what? That V1 over R2 plus V2 over R4 plus what's going to happen? V1 minus 15, so this would be a plus 15 over R1 plus V2, same thing, plus 15 over R3 equals 0, okay? All right. Again, think about how we would represent the voltage relative to the nodal voltages, okay? Going from V2 to V1 would have to generate 10 volts, okay? Going from 0 to V3 would have to generate 15 volts, okay? All right. So we have an equation here that looks perfectly fine. The nice thing is it involves V1 and V2. That's really nice, okay? We could solve for if we can get another equation of V1 and V2, we'll be ready to go. Now, interesting thing is we already have one, don't we? We already have a KVL equation. So technically speaking, we could then build a linear system and solve it. But just interesting to know what would happen if we went and looked at a KCL equation for the other supernode, because this illustrates an important concept here. So we're going to now do the currents coming out of that supernode, right? So let's do the ones, again, there's no particular order here, but if you're leaving this node where the voltage is 0 and you are going to V1, you're going from 0 to V1, 0 minus V1 over R2. So that current must be minus V1 over R2. Again, the voltage is always 0 at the ground, okay? Same thing here, 0 to V2 through R4, so you'd have minus V2 over R4, okay? And then if we're, again, coming up over here, we've got to go from V3 to V2. Again, all the currents coming out of the supernova. We took care of these two. Now we go left here, V3 to V2 over R3 using our NBA approach, and then V3 to V1 through R1. Sorry, V1. V3 minus V1 over R1. And that has to be equal to 0. Using the same knowledge of, but wait a second, V3 is just minus 15 volts. This would give us this equation. Minus V1 over R2 minus V2 over R4 plus, let's see what's going to happen. This is interesting because you're going to have minus 15 minus V2. So we could just say that's going to be minus V2 plus 15 over R3. Same thing will happen here. You're going to have minus 15 minus V1. So we could just subtract out minus V1 plus 15 over R1 equals 0. Okay. Now, if you look very carefully at these equations and notice you could multiply through by a negative all the way here because -1 times 0 is 0, you'd have the identical equations, okay? So what you have here are the same equations. Taking two supernodes in this case was redundant because it produced the same equations. In fact, if you were to make a matrix equation from these two, right, what would happen is your linear system would look like this. And this is good practice too. Suppose we wanted to represent the coefficient matrix that you would get. Well, if you took the top equation, you're looking for all the coefficients of V1. So you'd have 1 over R2 plus 1 over R1. So you look at all the coefficients that would be in front of the V1 and put it in that element of the matrix. And then look at all the coefficients of V2, 1 over 4 and 1 over 3. So 1 over R3 plus 1 over R4. And then everything that's left over would go to the other side. And that's the 15 terms, 15 over R1 and 15 over R2. And they'll have to be flip sign negative. So it'll be minus 15 over R1 minus 15 over R3. Then the bottom, well, the only difference is going to be negatives. The V1 coefficients, right, are just negative 1 over R2 minus 1 over R1. And then you'll notice you'll have the same thing here for V2, minus 1 over R4, minus 1 over R3. So it's just minus 1 over R3, minus 1 over R4. And then the 15 over R3 goes to the other side, the 15 over R1 goes on the other side, but the signs will be different. They'll be positive. So, and the point of doing this is that if you were in linear algebra class and you had a row that is a scalar multiple of another row, because this is just the same row, it's just a negative sign through, right? Well, what you would get is you would have an infinite number of solutions. There would be no unique solution for the nodal voltages, okay? This is also what's called because there's only one independent equation here, because the other one's a multiple of it, this is called a rank 1 linear system. Of equations, okay? So this is not useful because you need to have independence, and that you remember you get unique solutions for linear systems when the rows are independent. So it's fine to choose one of these. So the idea is choose KVL in one of these to build your linear system, okay? KVL is fine, or using the relationship between V2 and V1 as I illustrated, just purely from looking at how to define changes in voltage across the circuit, okay? But we have to be careful. And the next time, we're gonna do one more example and we'll illustrate how we can build a lot of equations and choose which ones we want to use to build our linear system for our nodal voltages. So let's do that. Now you're on the page 53. And in this case, we're just gonna choose one supernode, but we're gonna look through a variety of equations here to see what our choices are, okay? And again, when you see nodal voltages represented here and the voltage source in between, the best bet is make that a supernode, okay? So we'll go ahead and make that a supernode. Okay. And again, we're just going to go through a couple of options here, again, to get relationships between our nodal voltages. Paying attention to a couple of things, right? Noticing that your ground now, interesting enough, is over here now. So we might want to think about our polarities for the nodal voltages. And this voltage arrow for that V1, you're plus here and minus there. So if you're doing KVL and you come into the top of the arrow, you're going to be plus. If you're coming this direction, you're going to be minus for that nodal voltage. Same thing for V2. I'm just drawing some polarity arrows here. Same thing for V3, okay? In terms of minus and plus. So it's just good to get, the polarities for your nodal voltages straight, depending upon where your reference node is, okay? All right? Keep in mind, we know that the voltage at that ground is 0. So this node right here has 0 voltage, okay? Right? And you're going from 0 voltage to V2. The fact that this current source is coming from this direction and is directly connected to the ground, that means there will be no voltage here. There's voltage at V2, but there's no voltage on this current source, okay? It's going from 0 to V2, so the voltage changes from 0 to V2, so there's nothing there, okay? All right? So let's do a KVL loop, and let's just do a KVL loop counterclockwise just to be different. So we're gonna go counterclockwise. Let's do it on the top. So we're doing KVL on the top loop here. and see what equations we can get for our nodal voltages that way. Again, top loop, counterclockwise. Okay. All right. So if we're going counterclockwise, and again, we're only representing voltages, okay, that we are encountering, right? So in this case, for the nodal voltage V1, right, we're coming in, if we're going counterclockwise, we're coming into the bottom of the arrow, so that'll give us a minus polarity, so we'll have minus V1. Then we'll come into the positive polarity for that voltage source, so we'll be plus 10 volts. Then we're coming into the arrowhead of the nodal voltage of V2, so that's a plus V2. There's no voltage there, I told you, because of the grounding there, and that's it. Okay. Right? Again, this is going from this resistance is being connected to the ground, so there's no voltage here. There's voltage over here, but not on this side, okay? All right, so that's a nice equation. If we simplified that, we could say, well, that's the same thing as V1 minus V2 equals 10. That could be a very nice equation, okay? Just rearranging some terms there. Let's try KCL at node 3. Okay. Remember the approach of KCL is we're representing currents now, and we're representing all the currents coming out of this node V3 using our nodal voltage approach. Let's go this direction. We would go from whatever the voltage is there to V1 over R2, so that current must be V3 minus V1 over R2. Can do the same process. You would go from V3 to V2 through R3, so that's V3 minus V2 over R3, right? And then one more, right? We would go from V3 to ground to 0. So V3 minus 0 over 4. So we go V3 over R4 equals 0. A very nice equation there. Involves all three unknowns, okay? Now, 2 equations is not enough, all right? If you have 3 unknowns, 3 nodal voltages, and that's our goal, is we want a linear system involving all 3 nodal voltages, V1, V2, and V3, okay? The ground is here at 0, but there's voltage here, right? So this is not directly connected because of that resistance, right? So so we need another equation. So we're going to do 2 more. We're going to do the KCL at the supernode, and we're going to do KPL at the reference node. Let's go ahead and do the reference node, just to show you that you can do this. You haven't done this before. Suppose you wanted to do KCL at the reference node, okay? Because there's current coming out here, right? First current you notice coming out is 1, right? So there's a current there. Then you could represent current going from what, 0 voltage to V3, 0 minus V3 over R4. So we get minus V3 over R4. We'd also could go from 0 voltage to V1 through R1. So it'd be 0 minus V1, or we get minus V1 over R1, and that is equal to 0. Another really nice equation there, right? And we can actually simplify that one. Maybe we'll simplify it as what, V1 over R1 plus V3 over R4 equals 1, just pulling the node voltages over the other side. Now, technically speaking, we have 3 equations and 3 unknowns. The fact that this only involves V1 and V2 is fine. This only involves V1 and V3, that's okay. But now we get all 3 of them in this one. So we'll see about that in just a second. But let's just go ahead, for the sake of the argument, what would the KCL equation for the supernode be? Okay. Right? How many currents are involved? One coming up here, one coming down, another one coming down, and one coming to the right, right? So let's do the case of coming to, let's go above. So we're going from V1 to the ground through R1. So that'll be V1 minus 0 over R1, or just V1 over R1. We would also have V1 coming down and going to V3 voltage over R2. So we'll have plus V1 minus 3 over R2. Plus what? This current would have to be V2. We're going to do, yeah, V2 would go to V3. Let's go down. V2 to V3 through R3. And then finally, this current is represented as an incoming current, but as an outgoing current, it would be minus 1, right? Equals 0. And there we go. And so this is a perfectly valid independent equation too. None of these four equations are related to each other by just multiplying through by scalars and getting the other. So the idea might be, why don't we choose the first one, choose KVL and any two of the KCL equations. To form a linearly independent three by three system of equations. So the key adjective there is to linearly independent, right? Can't have multiples like we saw in the previous example. If we just, again, chose the first three, what would the equation look like? I illustrated, I mean, you could use any combination of the two of these and that one. It's just, what would the matrix equation look like? Okay. Again, the unknowns are here, those are the nodal voltages, and there will be a right-hand side vector. And our goal is we want a unique solution. Okay? And the only way we're going to get that is we get a non-singular coefficient matrix here, and that should happen if the equations are linear independent. So if we choose the KVL equation, the only term on V1 is a 1. The coefficient on V2 is a -1 in that row. There, you don't see a V3 term, so this coefficient is 0. The 10 stays here. So again, this is like inner products. This vector times this vector, this column vector times this row vector would give you this equation. How does that work? 1 times V1 plus -1 times V2 plus 0 times V3 equals 10. Again, that's going back to linear algebra class, okay? Let's write the matrix row equation for using KVL node 3. Well, again, what are the coefficients for V1? In this case, there's only one. It's going to be -1 over R2, okay? You see that? Look for the coefficients. R2 would be known, the resistances would be known, those would be real numbers. What about V2? Oh, there's just this term, -1 over R3. And then finally for V3, there are 3 terms, 1 over R2, 1 over R3, and 1 over R4. So be careful here how we write this. 1 over R2 plus 1 over R3 plus 1 over R4. Sum of 4 terms there, sum of 3 terms there. And then the right-hand side would have to be 0. There's no other value here, okay? Now for the reference node equation, there we go. This time, there's only 1 over R1 in front of the V1. There is no coefficient for V2, so we'll place a 0 there, and then we have 1 over R4 as the coefficient for V3, and that must be equal to 1, okay? So what we have here is a non-singular, or we could say invertible, coefficient matrix, because the rows and columns are linearly independent, okay? And again, you would have the resistances, you set the equations up and then use your matrix solver, MATLAB calculator, Python, whatever, and there's your right-hand side vector and it would produce the nodal voltages that we need. So lots of ways of creating current equations and voltage equations here. So I'm just trying to illustrate the fact that the supernode is one option. Sometimes you don't need it, but sometimes it's just as easy, and one could take the supernode and let it be one of the rows and it'll all be fine, okay? So in the next section, what we'll do is look at cases of applying supernodes where the current or the voltage sources are not independent. In other words, what if there's gain parameters? And that can complicate things on how do we know what the voltage differential is going to be, because it depends on something else, somewhere else, some other current or voltage elsewhere in the circuit. not always 10 volts, or, as we had in this case, right? So we'll do that next time.